Charlie, how's it going over here? I haven't heard a peep out of you in almost an hour.
Yeah, and we know how unusual that is. What are you doing that's keeping you so quiet?
Well, Jose, as you know, we're going to talk about scientific inquiry today. I'm just finishing my observations on one of the experiments I conducted this week. It'll show our audience how scientific inquiry works.
All I see is a mess of sugar and rotten bananas. Other than completely grossing me out, I'm not sure how this is going to help us understand scientific inquiry.
This coming from someone who's spending half an hour making lemonade. How's that going to help us?
Hold on, you two. Both of you are showing us exactly how scientific inquiry works and the fact that it is used by everyone every day. And I do mean everyone, including all of you out there. First things first, though, we need to explain what scientific inquiry is. Okay. Scientific inquiry is the process that scientists use to answer questions and learn about how the world works in an accurate and unbiased way. It uses the same reasoning we all do to solve problems and make decisions in our everyday lives.
Ever decide on what toothpaste to use, or which friend to call and ask over to your house, or figure out why a light bulb may not work?
Ever wonder how dew is formed, or what causes bananas to ripen faster?
Ew, that still grosses me out.
All these questions and problems can be answered using scientific inquiry. And here's how you do it. First, define a problem or ask a question. Then, form a hypothesis about what you think the solution is. Next, plan and conduct an experiment that will give you information you can use to solve your problem. When you're done with the experiment, gather and analyze the results. Then, form a conclusion based on those results. And finally, explain your experiment and conclusion to others. Charlie, why don't you start by explaining your experiment and go over each step one at a time?
Sure, Lori. Let's start with Jose's favorite, the rotting bananas. Now, I love bananas, but the problem is that after a few days, the last one in the bunch is always brown and mushy. So I asked myself, how can I slow down the speed that bananas ripen?
That's the first part of scientific inquiry.
Right. I then thought that the most likely cause was the amount of air around the banana, which made my hypothesis. The more air bananas are exposed to, the faster they ripen.
Stated simply, a hypothesis is an educated guess or a prediction based on the information you have at the time and what you think the answer to your question is. The key to a good hypothesis is that it must be stated in a way that can be tested by an experiment. For example, with the light bulb not working mentioned earlier by Jose, the hypothesis can be, the outlet is not working, or the lamp is unplugged, or the light bulb is burned out.
Next, I set up my experiment with the following items: 3 bananas from the same bunch at the same ripeness, 2 sealable plastic bags, and a paper plate for each banana. I placed 1 banana on a plate uncovered. I put another one inside an open plastic bag, and then sealed a third banana inside a plastic bag with all of the air taken out. With this setup, I made sure that the only independent variable in the experiment was the amount of air each banana was exposed to.
Hey, I know what variables are. They are the factors that have an effect on the experiment. The independent variable is the one thing you change in your experiment, while the factors that stay the same are called the controlled variables.
That's right, Jose. In Charlie's experiment, the controlled variables are the age and size of the bananas, as well as the temperature of the room. This way, the only difference for each banana is the amount of air it's exposed to. Having only one independent variable in your experiment is very important. Even with the light bulb problem, you wouldn't want to change the light bulb and move the lamp to another outlet at the same time. Otherwise, when you turn on your lamp, you won't be sure which variable caused the result you reached. So, what did you do then, Charlie?
Well, I let the bananas sit for 10 days, and I checked them every other day, taking notes on any changes I saw. And after 10 days, here are the results. The banana in the open air, as expected, is now way overripe and has turned brown. The banana in the open bag has also ripened quite a lot, but not as much as the one in the open air. The banana in the sealed plastic bag is still looking good enough to eat.
What you have observed is the last of the 3 types of variables, the dependent variable. This is the variable being tested that is reacting to the independent variable. In this case, the ripeness of the banana is the dependent variable. Now, all you need to do is form your conclusion.
Based on the data I observed, I feel that my hypothesis is correct. Air has a direct impact on how long it takes for bananas to ripen. The more air the banana had around it, the quicker it ripened.
And since you've explained your experiment so well to us, Others can now repeat it to get the same results. Then your hypothesis might turn into a theory.
Really?
Sure, a theory is a hypothesis that has been confirmed through repeated experimental tests. It explains existing facts and predicts new ones.
Then Charlie just proved how bananas ripen?
Not exactly. A theory itself is not a proven fact. There could be an experiment or possible discovery that would prove a theory untrue. In Charlie's case, she could come up with another hypothesis that questions whether there are other independent variables, in addition to air, that would cause bananas to ripen faster. One experiment could be placing an overripe banana inside the plastic bag with the unripened one. After all, as the old saying goes, one rotten apple spoils the whole barrel.
Okay, I get it. But what I don't get is how Jose mixing lemonade relates to scientific inquiry.
That, my dear, has to do with how scientific inquiry can be used in everyday life.
You know how directions on a can of juice or iced tea or lemonade mix say mix 1 cup into 2 quarts of water, more or less to taste?
Oh, I get it. You're using scientific inquiry to determine what mixture will make the lemonade taste best to you.
Yep, and here's what I've done so far. First, as Charlie mentioned, my question was, what amount of lemonade mix in 2 quarts of water will make the best tasting lemonade? My hypothesis was, if I put a half a cup of mix into 2 quarts of water, the lemonade will taste better than following the directions on the label.
Excellent! Please continue.
The controlled variable is the amount of water I use in each container, 2 quarts. The water must also be from the same source and be the same temperature in each container. The independent variable is the amount of mix I use, 1/2 cup in one container and 1 full cup in the other, like the directions. The dependent variable is how good the lemonade tastes. Then I conducted my experiment and I'm about to gather my results. First, the lemonade the way the directions say to mix it. Too strong, as expected. Not for the half cup mixture. Yuck, this tastes awful. Lori, the experiment didn't work. I used scientific inquiry. What happened?
Calm down, Jose. It worked perfectly. You just didn't get the results you expected. You see, regardless of the outcome, as long as you do things correctly, you'll always learn something. Science is not always about finding the answer. Sometimes it's about narrowing down the possible solutions. So in your case, you now know that a half a cup of mix is too weak, and the directions are still too strong for your tastes. Why don't you come up with a new hypothesis and make a new experiment using what you've learned?
Good idea. This time, I'll keep all of my controlled variables the same, but change my independent variable to be 3/4 of a cup.
Try it! Meanwhile, as Jose revises his experiment, we should talk a little more about duplicating your results. As we mentioned earlier, in science, the key is for anyone to be able to repeat the experiment to confirm your results. Otherwise, the experiment is not valid. The great thing about scientific inquiry is that it allows people to do just that. And once your results are proven over and over again, other scientists can develop theories to help the world advance and evolve. From using past medical advancements to making new life-saving medicines, to using a new kind of rubber to make a golf ball fly a little farther than before. Every advancement builds on past uses of scientific inquiry.
All done.
Great! Time to gather the results and analyze them.
Much better. This is just right.
And if I were making lemonade for Jose, I could duplicate his results so that it tastes good for him every time.
Exactly, Charlie. By the way, let's go back over to your other experiment. I'm interested to see how you use scientific inquiry in that one.
Okay, first of all sounds that we hear are actually waves of air created by a vibration, like this rubber band here. When it is stretched tight and I pluck it, we can see the band move back and forth as we hear it hum. Air molecules are vibrating out from the rubber band to our ears. However, we can't actually see the hum from the rubber band, can we?
Nope.
But then I asked myself, if I can't see sound, can I see the effects of the sound waves?
Ooh, good one.
Thanks. I started by gathering all of my materials, an empty cookie tin, a sheet of plastic wrap, a metal baking tray, a large spoon, sugar, and my rubber band here.
Note that Charlie has made sure she has all of the items she needs to conduct her experiment. This is a very important part of any science project.
I tightly stretched the plastic sheet over the opening of the cookie tin. I held it on with a rubber band. Then I sprinkled the sugar on top of the plastic. Now that I'm set up, I can test my hypothesis, which is, if I hit the baking pan with the spoon over the cookie tin, then I will see the sugar move around from the effect of the sound waves hitting the plastic.
Cool, let's do it.
Okay, here it goes. There, look, the sugar's dancing on the plastic. The faster I hit the tin, the faster the sugar moves as well. Note that there are no wires or trick cookie tins to create this trick. Just pure sound waves. Thank you. You've been a wonderful audience.
Okay, after Charlie has finished giving herself a well-deserved hand, let's show that experiment again, showing everyone what happened and how it uses scientific inquiry. First of all, here was her question and hypothesis once again.
If I can't see sound, can I see the effects of the sound waves? If I hit the baking pan with the spoon over the cookie tin, then I will see the sugar move around from the effect of the sound waves hitting the plastic.
Now, since the sound waves Charlie was creating were not loud, like say a jet engine, she created an experiment that would be very sensitive to vibrations. The independent variable here is the sound coming off the pan when hit by the spoon. As we already heard, Charlie has proudly stated the results of her experiment. Each time she hit the pan, the sugar would move, and she could even control how much the sugar moved as well. Therefore, Charlie's question has been answered in her conclusion that the effects of sound waves are seen with the dancing sugar. That effect is called, once again,
the dependent variable.
Lori, so far we haven't done any experiments that have relied on people to be part of the experiment. What happens when you need to do this? How are you going to control all the variables that people bring into your experiment?
Excellent question, Jose.
I'll say.
And I have an excellent answer. What you're referring to is the unwanted factor of bias in your experiment. Bias is when a person's feelings or opinions affect an experiment, resulting in false or inaccurate information. For example, you may be so sure that a medicine you take doesn't work, you can actually convince yourself that it doesn't, and vice versa.
Huh?
In an experiment involving, let's say, pain medication, the person who is the test subject may actually say he feels better, even if it really doesn't work, because that is what the medication was supposed to do. He tricks himself into thinking he feels better, and that makes it impossible for scientists to determine whether or not the medicine actually works. The most common way to fix this problem as a scientist is by using a placebo.
A what?
A placebo is used in experiments to test medications and ensure that bias doesn't ruin an experiment. It looks, tastes, and feels just like the real medicine, but it's fake.
Wow, we've covered a lot today.
You're right, Jose. Why don't you two recap everything we've discussed for our viewers, and I'll provide a few tips along the way.
Okay, I'll start. The first part of scientific inquiry is to come up with a question that you want to answer or a problem you want to solve. It can be something scientific, like my experiments, or an everyday situation, like Jose's lemonade.
The second part is to form a hypothesis. This is what you think the answer to your question will be.
Remember, this statement is not just a wild guess. It is always based on what you already know and can be proved or disproved with an experiment.
The third part is planning and conducting an experiment to test your hypothesis. A few tips to a successful experiment is to make a list of everything you will need in your experiment in advance. Only have one independent variable, and make sure that others can repeat your experiment to verify your results.
A quick safety reminder. It's always a good idea to check with an adult before doing any experiment, even if it's just to get permission to use all the lemonade mix. And also, to wear safety equipment whenever you use chemicals, heat, electricity, or anything else that might harm you if mishandled.
The fourth part of scientific inquiry is gathering the results and analyzing them. Even if the results do not match your hypothesis, you will learn something valuable if you did your experiment correctly. Did you know that Post-its were invented by someone who was trying to make a new kind of super glue? When it didn't work, the researcher used the glue to stick up little pieces of paper, and Post-its were born.
That's pretty neat.
Yeah. And the last part is forming a conclusion and then explaining the experiment to others, which is exactly what you two have done so well today. Remember, if your hypothesis is disproved, you can always go back and start again with the new information. And that's all there is to scientific inquiry.
Oh, I just realized that I have a soccer game in an hour, and I'm trying a new set of cleats to see if I have better footing during games than my other pair. See ya.
And I need to find out who I'm going to the movies with tonight. Bye!
Well, they're off to use scientific inquiry. Can you come up with everyday uses for it as well? I bet you can. See you next time.